Greetings everyone, my name is Daniel Stolfi from the University of Luxembourg. I am going to present the invited talk, Simulation-Based UAS Swarm Mobility Optimization. In this context, UAS stands for Unmanned Autonomous System. I work as a postdoc in the PaCOS group at the SNT, the Interdisciplinary Center for Security, Reliability and Trust. We are settled in the Belval campus at the south of Luxembourg, very close to the north of France. Actually, part of the green countryside in the picture is French territory. This talk is divided into 4 parts. First of all, in the introduction, I will describe our Haunted project and the motivations of our research work presented today. Then I will describe the Haunted Sim, a multi-swarm simulator we have developed for our project. In third place, I will present the different optimization processes we have followed, and finally, some conclusions and future work.
Let's start with the introduction by describing our motivations as part of our Haunted project. The Haunted project began in 2018. Our approach is divided into 3 main levels: interswarm, intraswarm, networking, and communication. The interswarm level was thought having in mind collaborations between swarms of vehicles, coordination between swarm members using pheromones, and evolutionary game theory are also included in this level. The intraswarm levels related to design and development of mobility models for vehicles using unpredictable trajectories based on chaotic mechanisms for exploratory patterns. And the networking and communication levels involves the use of adaptive clustering algorithms for highly reliable multi-hop communications, not only between vehicles but also with the ground control station. As it can be seen in the image, among UAS, we can find UAVs, UGVs, and UMVs. So far, we have worked with UAVs and UGVs, although we have an ongoing work using also UGVs. Unmanned aerial vehicles, which are also known as drones, can be multirotors, as quadcopters, or fixed-wing devices, having each class its own advantages and disadvantages. They have become commonplace devices in the 21st century. They can be found everywhere, from toys to military devices, while their cost can vary from tens to millions of dollars. The use of UAVs represents several advantages for the society, although there are some concerns about drones disturbing the privacy of individuals by flying above them and monitoring their activities. These flying devices are usually equipped with video cameras, radio, and variety of sensors and actuators. You can imagine that the numbers of applications is huge. UAVs' main advantages are the ability of exploring different areas, flying at a relative high speed. These eyes in the sky present also an excellent communication range, as usually there is a clear line of sight between devices. On the other hand, the flying time is short. Although it is longer in fixed-wing drones, they cannot carry heavy payloads and lack of stability in harsh weather conditions. Unmanned ground vehicles are the UAV's complement in the ground. They are also equipped with sensors, cameras, actuators, and radio communications capabilities. In this case, large heavy payloads are not an issue. They are more human-friendly, and when they are stopped, the power consumption is minimal, so their batteries stay alive for long. UGVs are a good complement of UAVs in missions, for example by providing transportation or behaving as a recharging station. The disadvantages are in this case a reduced communication range, especially by losing the line of sight, for example behind the wall. They are slower than UAVs and are affected by land conditions such as water surfaces, slopes, etc. Now I will proceed to explain our simulation approach and 3 mobility models that can be used with it. Experimentation with UAVs is subject to adverse atmospheric conditions. Their high cost also limits the number of members in a swarm, not to say that accidents such as collisions happen, and they may easily drain a project's budget in an early stage of the experimentation. Simulation environments can help with this matter, especially when addressing black box problems where a mathematical function representing the model is not available or it is very difficult to obtain. As our surveillance problems fall in this category, we have evaluated some of the existing simulators such as Gazebo, Webots, Argos, and VREP. We found that they were mainly focused on flying dynamics. Consequently, these simulations demanded high computing resources and the simulation times were too long, even when not using the graphical interface. We weren't interested in simulating propellers as we use commercial vehicles already designed. We weren't interested in modeling the surrounding houses, streets, etc. either, as since we needed very efficient simulations taking at the most a few seconds to finish, we decided to design and develop our own simulator. We call it Hunted Sim, as it was developed for our current project. The main features of our simulators are the capability of modeling different vehicles and their mobility characteristics, the implementation of a virtual pheromone map, very useful for our mobility models, the possibility of adding intruders and/or escapers to the simulation scenario, the implementation of detection zones in which vehicles can detect intruders. Among the available outputs, there are metrics like coverage, fairness, detection rates, etc. Additionally, there exists the possibility of sharing trajectories with other software packages, like APM Planner. This allows us to test the trajectories in real UAVs. We haven't evaluated the use of surrogate models so far, since the simulation times we are working with still allowing us to achieve good results in realistic times. Consequently, we prefer a more accurate model performing a detailed full microsimulation. We have developed a graphic interface which connects the simulator via socket in order to see in real time the simulation scenario. These are 2 snapshots of the simulation scenario from the graphic interface. At the left side of the screen we can see 4 UAVs and the corresponding pheromone trails. They have a detection zone from the onboard camera and there is an intruder at the bottom of the scenario, which is trying to reach its destination at the center of the scenario. At the right side of the screen, the UAV's trajectories and the area coverage were activated to be displayed. In this snapshot, we can see another different simulation scenario, showing at the top of the screen the simulation controls and at the right the evolution of 5 metrics: coverage, fairness, amount of pheromones, detection rates, and the minimum battery charge. This video shows an example of a swarm of 16 UAVs detecting intruders entering their surveillance area. Each UAV has its own detection area and pheromone trails. One intruder is entering the area at this very moment. The intruder's destination is at the center of the scenario. Note that this intruder is about to be spotted by this UAV. The rest of detections are taking place during the simulation time. Sometimes one intruder manages to avoid some UAVs, but it is finally detected. We have used 3 different mobility models in our research work, and other 2 are under revision right now. Actually, one of them has already been accepted for publication. The first mobility model is called CROMM, Chaotic Rosler Mobility Model, and it presents trajectories which are pure chaotic. The second is called CACOC, Chaotic Ant Colony Optimization for Coverage, which combines CROMM with virtual pheromones. And the third is ABISS, Attractor-Based Inter-Swarm Collaborations, where CACOC is complemented with vehicle attractors for fostering inter-swarm collaborations. I will briefly describe each model in the following slides. CROMM is pure chaotic. That means that the decision variable, rho, takes its values from the first return map of a chaotic attractor. Chaotic systems are very sensitive to their initial conditions and their implementation. That makes the values of rho unpredictable for an external observer, as it can be an intruder trying to trespass a restricted area. The next moving direction for each vehicle is calculated by CROMM at each simulation step. As a result, the vehicle can be moving ahead, turning left or turning right. The three options are equiprobable. CACOC combines CROMM with virtual pheromones. It is useful to avoid visiting the same spots very frequently and in short time. As pheromones eventually evaporate, those spots are likely to be visited again. If there is no pheromone in the neighborhood, CACOC uses CROMM as described in the previous slide. On the contrary, the probability of moving towards an area with pheromones is inversely proportional to the amount of pheromones on it. We have proposed three parameters to the original CACOC to adapt it to different scenarios and improve its detection rate and area coverage. Last but not least, we have ABISS, a mobility model that combines CACOC with the use of attractors. It was thought to improve the area coverage where there are unreachable zones in a scenario, for example, a water surface that cannot be accessed by UGVs. For example, when a UGV finds an unreachable zone, it leaves an attractor for UAVs. When a UAV detects that attractor, it moves toward this attractor according to a parameterized probability instead of continuing with its own trajectory. This inter-swarm collaboration adds 4 extra parameters to ABISS, as shown in the table on the right of the screen. All these parameters need to be optimized to get the best performance from our surveillance proposals. In this section, I will present 3 different evolutionary approaches involving parallel executions and evaluations. This slide sums up the parameters of CACOC and ABISS. Each system can be optimized by using the same parameters for all the UAVs, but we have opted by tuning each vehicle independently. It implies more complicated algorithms, larger optimization runs, and using parallelism to get results in realistic execution times. Of course, the results are also better when the system is optimized at such fine-grained level. The first selected algorithm is a genetic algorithm, which is the most popular evolutionary algorithm. Genetic algorithms simulate processes present in evolution, such as natural selection, gene recombination after reproduction, gene mutation, and the dominance of the fittest individuals over the weaker ones. A typical GA consists of a population of mu individuals from which a subset is selected using a selection operator. Then, these individuals are recombined using a crossover operator to obtain a new set of lambda individuals based on the original population. After that, a probabilistic mutation is applied, introducing little modifications to the individual's chromosome. Finally, after evaluating the new offspring, the replacement operator selects the fittest individuals to replace the former population. We have chosen an evolutionary-inspired approach for solving this difficult real problem, which requires high evaluation times and has a huge search space that is very difficult to explore using exhaustive methods. In our problems, there is no analytic equation, thus traditional methods are not viable. Since we work with population of individuals, the evaluation of each generation can be easily parallelized, noticeably reducing execution times. In our approach, we work with population of 20 individuals, which represent 20 configurations for the vehicles, and have to be evaluated by using 20 parallel simulations. Our initial prototypes were programmed in Python. After improving our original code using Numba for the more demanding functions, we have moved to C++ and POSIX threads, reducing the execution times even more. Our experiments were performed in the HPC facilities of the University of Luxembourg, which allow us to use different numbers of nodes and cores to get the best performance of our algorithm. The average speed up we have obtained was about 14.6 after the parallelization of the fitness function of the genetic algorithm, evaluating 20 individuals concurrently. A different approach was followed in the next algorithm. The idea was to optimize each UAV's parameters independently by using its own dedicated genetic algorithm, and then evaluate the whole system using the UAV's configurations altogether. For doing that, we have designed a cooperative coevolutionary genetic algorithm, which runs n GAs in parallel. This slide shows parallel GAs as part of the whole CCGA. For example, the solution vector 1 is to be evaluated. The rest of the configuration vector is taken from the rest of the populations to build the full configuration vector. There are two ways of doing this. One by taking the best individuals in terms of fitness from the other populations, or a random sample from each population, which sometimes works better depending on the problem. Then the full configuration presenting the best fitness is selected and its fitness value is assigned to the individual containing the solution vector 1. The rest of the process is followed for the rest of individuals in the population of GA1 and for the rest of the GAs in the algorithm. As you can imagine, the implementation of this system is challenging, as all the operators have to be applied to all the populations before beginning with the evaluation itself. Although we didn't do it, it is possible that each GA evaluates its own population in parallel as well, providing there are enough execution cores available. For example, for H UAVs and the population of 20 individuals, 160 execution cores are needed. Our last approach consisted in a predator-prey model. In this case, the UAVs are not only trying to increase the area coverage, but also they have to spot the maximum number of intruders. On the other hand, there are no intruders in this scenario that randomly enter the surveillance area and try to reach the base in the center of the map. There are 5 parameters for intruders: the arrival point defined by the edge and coordinate, the moving speed, the arrival time, and the intensity of the repulsive force. As we have seen in the previous video, intruders try to evade UAVs by finding alternative trajectories and detours in order to get access to the base. In order to optimize the predators, but also the prey, we have proposed a competitive coevolutionary genetic algorithm. In this case, the COMPCGA contains 2 genetic algorithms. One is for optimizing the UAV's configuration and the other for optimizing the intruders. Each population evolves isolated from the other until 10 generations passes. At that moment, the best adversaries are exchanged between populations and each best configuration has to evolve to defeat the new opponent. Here we can see the blocks diagram of the COMPCGA. One GA is for optimizing the UAV's configuration and the other for optimizing the intruders. The UAV's configuration is evaluated using the best intruder as part of the configuration of the simulator. The same happens with their counterparts. Both GA's executions are parallels, and again, each population evaluation can be parallel too. After the execution of the COMPCGA, a master tournament is performed between the best specimens exchanged between GAs. The best configuration for the UAVs will be the best configuration which beats the higher number of intruders configurations.
As conclusions, we have presented Hunted Sim as part of the Hunted project. Our mobility proposal includes 3 mobility models for UAS. We have used parallel evaluation of the mobility scenarios, and our simulation-based optimization approach allows us to obtain efficient swarming configuration for surveillance, do it while significantly reducing evaluation times. As future work, we want to test our proposal in different bigger scenarios, increasing even more the number of intruders. We want also to increase the realism of our approach, adding a communication layer, and of course testing all our mobility models in using real drones. That's all. Thank you for your attention. I will be very glad to answer all your questions. So please do not hesitate to ask me them by writing to my email address. Be safe.